In this particular video, we'll be looking at missing equilibrium concentration, just like part 2. But here we are going to be giving you the initial concentration rather than giving you the equilibrium concentration. Part 2 of the video, we gave you the equilibrium concentration of the reactant and the products, or maybe just one of them. And then we gave you the Kc value. Over here, the equilibrium concentration is what we're going to try to look for by giving the initial concentration. If you see the word initially within the problem in itself, you might want to think about utilizing the ICE table, or the initial change and the equilibrium concentration table. So let's dive into this particular example as we solve this problem. Brace yourself, make sure your calculator is ready because it will be quite a bit long calculation. Under certain conditions, the equilibrium constant Kc for decomposition for PCl5 into PCl3 and chlorine is 0.0211. What are the equilibrium concentration of PCl5, PCl3, and chlorine in a mixture that is initially contained by only PCl5 at a concentration of 1.00 molarity? So initially, or I, you only have PCl5, meaning these are all 0. As time passes, there is a change, and then it will diminish in the reactant by X. But for PCl3 and C2, it will increase by X. Since this is all 1:1:1 ratio, that's how I know they're all in X. Now, if it was 1:2:1 ratio, then it would be negative X, 2X, and 1X. Now, the equilibrium, or E, is represented by what goes on the top plus what's on the bottom. So what's on the top, that's 1.00, plus what's on the bottom, which is minus the X, or I could just write minus X. So over here on this one, it's 0 plus the X, which is just X. And then for here, it's 0 plus X, which is X. Now let's go ahead and write the concentration, equilibrium concentration setup. So Kc is equal to the product, which is PCl3 and Cl2, all over the PCl5. Okay, now that we have this so far, we can actually plug in whatever we know so far into this particular equation. For example, PCl3 concentration at equilibrium. How do I know it's at equilibrium? Because it's represented with K. At equilibrium is X. Same for chlorine, it's X, and then for PCl5 is 1.00 minus X. So we'll go ahead and put that in, X times the X all over 1.00 minus X. Also, we know Kc value, which is 0.0211. I'm going to kind of lump this up a bit by squaring this both sides, by squaring. X squared is equal to 0.0211, and we have 1.00 minus X on the bottom. I want to get rid of the bottom, or the denominator, so I'll go ahead and multiply this by both sides. And if I rearrange this and to rewrite it, I'm going to go all the way to the top here, it would be 1.00 minus X, parentheses, 0.0211 equals X squared. At this point, I can already see that this is forming into the, it will be nice setup for a quadratic formula in a moment. For now, I want you to go ahead and distribute this 0.02211 to both sides, this one and here. We're going to distribute it by multiplying. Minus 0.0211x. We'll leave one side all 0, and the other side, we're going to put all of the values on the other side. What that means, we're going to put this one on the other side, and we'll put this one on the other side. In order to do that, we have to subtract this, and then this one we have to add it. So we'll have 0 is equal to x squared plus 0.0211x minus the 0.0211. Now we have a setup that looks something like this. 0 is ax squared plus b squared, bx, I apologize, minus c plus c. Okay, it looks very something like this. Okay, and the reason why I put this is because we're going to put this in the quadratic formula. Quadratic formula is as follows. So I'm going to sing as I write this particular equation. It's kind of hard to memorize the quadratic formula, but I feel like if you have this song sort of in your head and memorize it, then it'll be fine. This is something I utilized since high school, and I hope this would help you as well. So the song or the music I'm about to sing goes like this. X equals negative b plus or minus square root b squared minus 4ac all over 2a. So that's my singing for you. There's a reason why I didn't join choir. All right, so here this b represents this value that is the coefficient in front of the x. This a represents the coefficient that is in front of the x squared, and c represents the value in the very end. In front of the in front of the x or the b is negative 0.0211. I'm plotting these values in right now. 0.0211 to the second power minus 4a. What is a? Well, in front of the x squared is actually 1. Okay, there is a 1 there, but it's not showing, so it's 1. And then c is that negative 0.0211. All over 2a. What is a? Again, it is 1. We're going to go ahead and put this into our calculator. In our calculator, I'm going to target the ones that's underneath the square root first, because that's much easier to work with. So that would be 0.0211 to the second power. Okay. And then we're going to go ahead and subtract that by the whatever multiplication that was on the right, which is 4 times the 1 times the negative 0.0211. Then close the parentheses, and I get that value. Then we're going to square root. You press second to the x squared, which is the square root, and then second answer, that gives you the answer that is right before. If I press that, then I get this value. So let's go ahead and write this value. 0.2913 plus or minus negative 211, and then bottom is 2. Now here you're given the option either to add or to subtract. Because the x cannot have a negative value, we're going to always have to shoot for the positive one. And so therefore we have to use a plus. If we use a negative, the whole thing will become negative. So we'll go ahead and erase the minus sign altogether just to get rid of that, and then to avoid confusion, and we'll calculate the rest. Negative 0.0211 plus 0.2913, and then divided by 2. So we get the value of 0.135. So x is equal to equal to 0.135 molarity. Well, of what does this mean? X, right? This X represents chlorine, and this represents the PCl3 at equilibrium. So this is concentration of Cl2 and PCl3. So we got the reactant component. What about the this is the product component. What about the reactant component? Well, the reactant is PCl5. And you see the concentration at equilibrium is 1.00 minus the X. We know X, which is 0.135. So if we were to subtract the two and to round off, we would get 0.87. 0.87, yeah. 0.87 with the correct sig figs, molarity. And so that's the concentration for PCl5. Go ahead and try this particular learning check and then come back and check the key. I will lead you just only up to the ICE table for now, and then I hope that you're able to connect what you have learned so far utilizing the quadratic equation to find out the final answer. So let's go ahead and set you up with the ICE table. A 1.00 liter flask filled with 1.00 moles of hydrogen and 2.00 moles of iodine. The value of equilibrium constant for the reaction of hydrogen and iodine reacting to form hydrogen iodide is 50.5 under the given conditions. What is the equilibrium concentration for hydrogen iodine and hydrogen iodide at equilibrium, right? We're looking for the concentration for all three values. Now, I'm going to again set you up before you begin, set up the ICE table. In the very beginning, you have 1 mole of this, okay, in a 1 liter flask, okay? What that means is for H2, you have 1 mole of the H2 all over 1 liter. Well, that is the same as 1.00 molarity of H2. So in the beginning, you have 1.00. For iodine, it tells you have 2.00 moles of I2 over 1 liter. That means this is 2.00 liters. Molarity of I2. So this is really 2.00. Now we have 0 of HI since no product has been formed. There is a change in that the reactant diminishes or minus the X. Since this is 1 to 1 to 2 ratio, we will end up having 2X here, positive 2X. So at equilibrium, you have 1.00 minus X. Here you have 2.00 minus X. And here you have 0 plus the 2X, which is just 2X. Okay, so now that we have ICE table filled out, hopefully you are able to set up for KC and also do the rest. So finally, the KC would be the HI to the second power, and you have H2 and I2. A little more complex than before. So you're going to take all of this and put them in here, okay? You're going to put them in here. You're going to do some distributing and all that fun stuff. And then come and check this particular video for the complete full version of the key that shows you step-by-step problems. Something to note in this particular equation and this particular entire calculation is the towards the end when you look at the quadratic formula and whether to utilize plus or minus. In the example prior to this, we had utilized the minus or the plus sign, and that's because we wanted the x value to be always positive. But here, whether you use the positive or the negative, you'll end up with the positive value. So which one do we use? Well, if you were to calculate utilizing the positive, you will get an x value that is greater than 1. If it's greater than 1, what's going to happen is if that's greater than 1, then that means the change in the h, right? If it's greater than 1.00, that means the equilibrium concentration will end up being negative. So because that x value is greater than 1. But if it's less than 1, like in this scenario, if I were to use the minus, right? 151.5 minus the 64.54 divided by 93 is 0.94. And this works out nicely as if you were to plug it in back into the equilibrium concentration equation. So therefore, I use the minus rather than the positive. Now, these are the three. I would say this is probably one of the most challenging out of all of the calculation as you have done so far. But if you are able to climb this particular mountain, then I think you're good to go and ready for the next section. In the next section, this gives you a very simple, rather, calculation, although you might think, oh no, another quadratic formula. And that's because of this Kc value being quite low. It's 10 to the negative 10 power. In this scenario, you will see how this particular equation or to solve this problem will be much, much simpler than the prior. Here it says, what are the concentrations of all of these three at equilibrium of 0.15 solution of HCN? So here you have HCN, and maybe this is not as clear. I mean, initially. So we're going to use the ICE table, and the HCN is 0.15 molarity in the beginning, and you don't have any of the product. Okay. Now for C, the change, so negative X, and this will become positive X. So equilibrium is the top plus the bottom. So these are all X's. Okay, and my Kc therefore is concentration of H plus, concentration of Cn minus, all over the concentration of HCN. Okay, so far so good. Then we're going to go ahead and plug in all these values. Here's x squared because this is x and H is x and Cn is x as well, all over HCN, which is 0.15 minus x. And now we have on the left side 4.9x times 10 to the negative 10. Now, when the Kc value is very low like this, okay, then we are going to ignore this minus x. We're going to see, we're saying that the change isn't very much, right? When an equilibrium concentration is very little, that means that we can sort of say the reaction barely goes forward, okay? It just maybe teensy, so we can ignore that negative x change value. So if we ignore this entirety, then we have x squared 0.15, 4.9 times 10 to the negative 10. And then I'm going to multiply 0.15 both sides. And if I were to do this, then x squared is equal to whatever these two values are multiplied by. So let's calculate this out. 0.15 times 4.9 times 10 to the negative 10. That will give me 7.35 times 10 to the 11. Which is equal to x squared. Right? Double check. Yeah. Okay, now we're going to square root this. Square root both sides. And so x will then equal to second square root, second answer, close it, and then enter. Get 8.6 times 10 to the negative 6, I believe it was 6, right? Yeah, 6 molarity is what it's equal to x, okay? So that's the concentration for x. What is x? Well, x represents the H plus, and for concentration for Cn minus, okay? All right, so that's for this guy over here. What about for HCN concentration? Well, that's 0.15 minus x, which is 0.15 minus the 8.6 times 10 to the negative 6. So we'll go ahead and put that into calculator too. 0.15 minus what we had before, and that gives me 0.15. So it's really, there was barely any change, right? It's very, very small value. So if I were to round this off, it's actually 0.15 just as is. So that you could now tell that really you don't, it's very small amount in order for this HCN to be diminished. So hence why the Kc value is so little, hence why we were able to ignore the negative x. All right, let's go into the next video, or next learning check here. And this one, I'd like for you to try on your own. What are the equilibrium concentration in a 0.25 molarity NH3 solution? So that's how much it started initially, okay, for NH3. And then it gives you the Kc value. Now notice that the Kc value is also very small. So when do you determine what is like the turning point where you can start ignoring that negative x value? Well, if you have a Kc value anywhere lower than 0.001, or also known as 1.0 times 10 to the negative 3, you can pretty much start ignoring it. And there's no actual cutoff line, but that's the general trend. So try this and come back. Here is the key.